Hello. It's science o'clock. I know it's half term, but some of you asked for some help. So here are the questions that I set for you, and I'm just going to go through them, telling you how to do them. Hopefully, you've been able to do these things, and if you haven't, well, let's just do it together, okay? So we start off. This circuit was set up as shown in the diagram. Here we have 4 cells, got an ammeter, we got a current here going this way, 0.2 amps, and a current going this way, 0.1 amps. So arrow, there are all the arrows on there. Each cell provides 1.5 volts. What is the total potential difference provided by the 4 cells? Well, 4 times 1.5, 3, that's 6 volts. Easy. 1 by 5 plus 1.5 plus 1.5 plus 1.5. Done. What is the potential difference? So, what potential difference is dropped over the 60 ohm resistor? It sounds like a really confusing thing, but actually it's just saying what is the value of the voltmeter across the 60 ohm resistor. Well, if you've got 6 volts coming from here and the 6 volts travel down along here, they can either the electrons carry the 6 volts, so they can either go through this way and be used up in the bulb, or they can go this way and be used up in the resistor. But either way, you get 6 volts in the resistor and 6 volts in the bulb. What is the current reading on the ammeter A? Okay, so here we need to remember that current splits as you go around the circuit at different junctions, and it comes back together. So we've got 0.2 going this way, 0.1 going this way, so 0.2 is here, 0.1 is here. As they join back together, we get 0.3, because the two currents have been separated by the 2 different roots, and then they come back together as they go back into the cell. So 0.3 amperes. What is the resistance over the bulb? The resistance, so you need to use the equation V equals IR. We need R, so V IR is the little triangle. Doot, doot, doot. And if we do V over I, that gives us R. So the voltage is, as we just said, 6 volts, because it's 6 volts in each, and I, what do we want, the bulb, so it's 0.2. Can't do that maths in my head, because can't. 6 divided by 0.2 is 30 ohms. Nice. Let's do question 2. Turn over to question 2. Calculate the total resistance of the series circuit. When you have 2 resistors next to each other, here, here, it's actually almost, no, it's not almost, it's exactly the same as having one big resistor. So it's just 9 plus 6 equals 15 ohms. Calculate the potential difference in the circuit. It's the same equation as before, V equals IR, but this time we know V and we know R, so 0.3 times 15. 0.3 is the current, I, because it tells us there, and R is the resistance, so 0.3 times 15 is 4.5, what are we after? Potential difference, so it's volts. A resistance of a 24 watt 12 volt filament lamp depends on the current flowing through the lamp. For currents up to 0.8 amps, the resistance has a constant value of 2.5 ohms. Use the equation which relates potential difference to resistance and current to calculate the potential difference across the lamp when the current is 0.8 amps. Okay, so let's just do P, I, V, R. Is there anything else it gives us? Okay, so we've got P is 24. We've got V is 12. It wants I to be 0.8 amps. We don't know which potential, so let's scrub that off. We know R is 2.5 ohms. So what do we want? We want V we could do V equals IR. Seems quite simple. We do 0.8 times 2.5. It's only worth 1 mark, so gives us 2 volts. Seems quite low. A filament lamp depends on the current flowing through the lamp. For currents up to 0.8 amps, the resistance has a constant value of 2.5. Use the equation which relates the potential difference to resistance and current to calculate the potential difference across the lamp. That's it. Easy. Right. Let's go across to the next one. Below is a diagram showing an electric hob. When all 4 heating elements are switched on at full power, the hob draws a current of 36 amps from 230 volts, mains electrical supply. Notice here's the main supply. Each of these heating elements is in parallel, okay? When all 4 heating elements are switched on, the hob draws a current of 36 amps and 230 main supply. Calculate the resistance of one heating element when the hob is switched on at full power. Wow. Okay, that's tricky. So, right, so we have 4 hobs, okay? 4 hobs like this, and we're going to assume each of them is the same. We're going to assume each hob is the same. Now, the electric current leaves the supply, travels down here, and then it gets here. Then it has to choose to go either this way, or this way, or this way, or this way. It can choose to go which one of the routes. Now, if they're different resistances, it means if they're different resistances, it means like the more current will go the easier route, and less current will go the harder route. We go if there's the same, we can evenly split. So 36 divided by 4 equals 9 amps in each one. If we get 9 amps in each one, 9 amps in each one, so we know B equals IR. We know, remember, as I said with the previous question, the electrons, in a parallel circuit, you get the same potential difference across each branch. So this branch gets 230 volts, this branch gets 230, this one gets 230, and this one gets 230. So we do V over I, and it equals R. So 230 over 9 equals, gives us, we round up to 26 ohms. I think that's right. 3 marks. A thermistor? A thermistor's resistance is measured with changing temperature, as shown below. What is we have some cells, doesn't tell us how many. We have a current of 0.025 amperes. We have a voltage of 9 volts. It's at 20 degrees. It's in water. There's Bunsen burner. What is the resistance? Okay, so again, it's the same equation. V equals IR. So V over I equals R. So 9 divided by 0.025 equals 360 ohms. That is the worst omega sign I've ever drawn, and I apologise. As the temperature of the water increases, the resistance of the thermistor decreases. Sketch and draw the graph of current versus temperature for this thermistor. So we'll put T on the bottom and we'll put I on here. So we'll just do this. That is an I. And that is a T. So as temperature increases, so that's going this way, as temperature gets hotter, the resistance increases, so the current goes down. In fact, that should probably go down to 0, but just didn't. Oh, I've just done it the wrong way. Misread. Sorry. Oh, that's the mean for that to do. this is T. It says, as the temperature of the water increases, the resistance decreases. Okay, so if the resistance is decreasing, then the current's going to increase. So this is I. So it's going to go, well, it's either a straight line like this, or they're not normally like that, but something like that. But either way, the current is going to increase as temperature increases. I apologise for the mistake before. Give myself a warning. Yeah, there we go. We're on to a different section. Fill in the gaps. To complete the sentences, use words in the box to help you. The letter I is used to represent current flowing through a component in a circuit. The letter V is used to represent potential difference. I'm just going to write pot diff because across the component. The current potential difference graph, IV, could be used to find the resistance. Run out of space again. The current is plotted on the Y and the potential difference on the X. The circuit must contain an ammeter to measure the current and a voltmeter to measure the potential difference. Label the components in the diagram below. This is an ammeter. This is a voltmeter. This is a resistor. This is a variable resistor. And this is a cell. Describe how the circuit would be used to collect readings so that a current potential graph could be plotted. So, set up circuit as shown. Move the variable resistor. We'll call it the slider. It's one of those. I haven't got anything that looks like it. It's like a big solenoid, a big coil, and then there's a slider that goes across the top, and you move that, and that changes the resistance. Move the variable resistor slider, small amount. Record V and A, so new values of voltage, new values of current for multiple values. Record V and A for multiple values. Plot graph. No? Oh, why is that still working? There we go. Come on. Come on. There we go. The current potential difference graph below shows the relationship between current and potential difference for a resistor. State the current flowing through the potential difference across when it's 2 volts. So here we have 2. Let's go up. That is here. So go across and it reads 0.2 amperes. State the potential difference across the resistor when the current is 0.3. Well, it's 0.3, so we go down. So we have 3 volts. Determine the resistance of the component. So V over I equals R. So we could pick either of those values. So when you had 2 volts, you had 0.2. 2 equals 10 ohms. Again, I did another awful. Oh, I'm not very good with this pen. Gosh, is this still going? The current potential difference is plotted for a component. Identify the characteristic, the component which this graph is. Identify the component for which this graph is the current potential difference characteristic. This is a bulb. We can tell because it levels out. After a while, when it gets here, no matter how much potential difference you put in, the current doesn't go up. That's because it's got hot, and as it gets hot, the resistance increases and no more can flow. Identify the component for which the following graph, for this one you'll just have to memorize. This is a diode, or you could say an LED, which is a light emitting diode. Fill in the spaces with the words from the box. Power is the energy transferred by each device each second, and is measured in watts or joules per second. So I can make this a bit bigger. A machine with a high power rating will transfer a large. Did I say large? Yeah, large is an option. A large amount of energy each second. Power is calculated using the equation. Power is energy over time. For electrical devices, power can also be used calculating this equation. Power is current times potential difference. P equals IV. Calculate the power ratings of each of the following devices. A hairdryer which converts 4,000 joules of electrical energy every minute. Okay, so 4,000 joules. Sorry, 40,000 joules divided by the time. Now don't do 1 minute, because 1 minute is not the time we do 60 seconds. So 40,000 divided by 60 is 666.6. 666.7 watts is the devil's hairdryer. An electric iron converts 720,000 joules in 10 minutes. So 10 times 60, 720,000 divided by 600 equals 1,200 watts. A microwave which uses 1.5 joules of energy to defrost a chicken in half an hour. 1.5 times 10 to the 6 all over. We've got to do 30 times 60. 30 minutes and half an hour. So 30 times 60 is equal to 833 watts. Nice. Go on. Oh yeah, we're on the last page. Sweet. Use the equation power is current times potential difference to fill in the missing values in the table. So P equals IV. So P IV. So for power we just do this times this. 1.8 times 230. 414. For power, potential difference, we do power divided by potential difference. 850 divided by 12. So really, what's that? 850 divided by 12 PIV. 70 amps? Something doesn't seem right there. What have I done wrong? PIV. Power divided by potential difference gives us a current. Okay. And that power divided by that current, that divided by that equals 333 volts. These are just random numbers, which obviously someone's chosen. They're not really usual. If you have something with a current of 70 amps, don't go anywhere near it. That's truly terrifying. Something's very wrong. A television has a power rating of 160 watts. A light bulb has a power rating of 40 watts. A dishwasher, 1,150 watts. Calculate the total energy transferred by these three appliances if they are used for a period of 4 hours over the course of a day. Okay, so we have to do power times time equals energy, and we do that for each individual one, and then add them all together. I'm going to sneeze. Excuse me. So let's do the TV. 160 times how long? 4 hours. So that's 4 times 3,600. That's how many seconds in an hour. Plus 40 times 4 times 3,600 plus the dishwasher. Why would you use a dishwasher for 4 hours? How many dishes have you got? 1150 times 4 times 3,600 equals, I have to do all of these. Actually, so we got 160 plus 40 times 4 times 0 equals, what's that in standard form? Where's my, so it gives us 1944000 joules, 119.4 megajoules. Nice. This sticker was found on a casing of an electrical appliance. Model KOT500, 230 to 240 volts, 50 Hz, 1100 to 1200 watts, Q00194, made in China, 139. Use information in the sticker to determine the minimum current it will use. Okay, so P equals IV, so P over V equals I. So we need to do the current, the power divided by the voltage. So what do we want? The minimum. So so we do the smallest power divided by the biggest voltage, gives us the smallest current, 4.58 amps. The maximum, or we'll do it the other way around, 1200 divided by 230. 1200 divided by 230 equals 5.2 amps. The average time to transfer 4 megajoules. So power times time equals energy. So we do power over energy, that equals time. So the average power, we'll do halfway between the two. 1150 divided by 4 times 10 to the 6, because that's mega. 1150 divided by 4 mega is what have I done wrong there? Power times time. Oh, I did the equation wrong. Silly sausage. Energy over time equals power. So energy over power. So I did it the wrong way around. Power times time equals energy. Yeah. So 4 times 10 to the 6 all over 1150. 4 mega divided by 1150 equals 3,478 seconds. Hopefully that was a bit useful, and if not, just tell me to stop bothering. Okay, love you, bye.